Hello and welcome to our first main lecture for stats. Before we get started, I do want to talk about a few things real quick about the pacing of what we're going to go through this semester. So each and every one of you is a master's student. So you're beyond what undergrads are in expectation. At the same time, most of you, if not all of you, have either had a stats class, a research methods class before, something where just about everything we cover this semester shouldn't be brand new to you. Because of that, I'm going to go through it at a faster pace than many people would be okay with, especially people who maybe this is their first stats class. That being said, I really want to emphasize that if you feel you're falling behind, if you feel I am going too fast, please send me a message so that I can either slow it down for you or slow it down for everyone, or just go over the stuff that maybe you feel you're falling behind on. I don't want these lectures to be so slow that you're getting bored with it, because again, this should be mainly almost review for most of this semester or parts of this semester, especially this first set of slides when we just look at the basic almost research methods side. So because of all of that, again, if I'm going too fast, message me, but I am going to go faster than I normally would just because you're all master's students. You should already know some of this. Okay, so what is the sequence of events for research in the behavioral sciences? So number one, we need to identify our problem or our question. So I say, how would you do this? This is where you might read a research report out there. You might see something in the news. You might see someone act or behave a certain way. So this gets you thinking, and then you think, okay, well, I want to know why they're behaving that way. Or is that typical? Is that behavior typical? So from that, we form a hypothesis. This hypothesis, we hypothesize based on the previous stuff that's out there, the previous research, the previous information we have, information that we may have in our brain about previous observations. We form a hypothesis. We then hypothesize that, let's say we hypothesize people are going to, in general, act a certain way. From there, we design and run an experiment, an investigation. That's the longer drawn out part, but that gets us to the main thing we're doing in this class, which is where you analyze the data to test these hypotheses. So you've now seen something that made you think, oh, I wonder if everybody does that. You formed a hypothesis that everybody does indeed do that. Then you designed and ran an experiment. You got a random sample. You tested people in situations where they could or could not do the thing you hypothesized. You recorded whether they did it or not. Then you analyze the data. You are then testing to see if, in general, in your sample, did the people in your sample, in general, do what you hypothesized. Then from that, you draw conclusions about that. You then take that information from your sample, and you make and look at implications on the larger population. Then after that, you communicate the results. This is where you publish it, present it in a poster, present it at a conference. And if you're really ambitious, then you replicate it, you extend it beyond that. Let's kind of look at a visual for that. So you've got your population. You've got your population, that's everyone. One of the issues is that we generally can't do a measure on everyone in the population. That's what's called a census. Census is a rare thing to do when you're looking at the context of large populations. So when we're looking at population, we've got Greek letters. So these are the Greek letters you'll see throughout the semester. I'll bring them up again and point them out when we get there. Because you cannot draw or you cannot test everyone in a population, what you end up doing is taking a sample of the population. And from the sample of the population, You have letters, which are your descriptive statistics. Your descriptive statistics, and we're going to kind of show the difference here, and in just a little bit we'll kind of get back to that. But your descriptive statistics are basically just describing your data, describing your sample. And then from there, we use inferential statistics to make inferences from the sample to the population. So we take a sample from the population, and then we make inferences about the population based on that sample. And how do we make those inferences in inferential statistics? We make those inferences based on probability theory. That's why we're going to spend 2 full weeks on probability theory, is because probability theory is what allows us to take our descriptive statistics from our sample and use inferential statistics about the population. There is a lot of terminology we use in stats. Hopefully all of you have seen this stuff before, but let's go through these. We're going to look at different types of statistics. We're going to look at population versus sample, experimental design, measurement, limits, rounding, statistical notation, the basic stuff of kind of giving an overview of what we're going to do starting next week. So again, hopefully you've all seen this before, but what are we looking at here? Well, the first thing we're going to define is a variable, and a variable is anything that can take on a different quantity or quality. We could have the variable of a auto manufacturer. So the variable is auto manufacturer. Is it Ford? Is it Chevy? Is it Toyota? The variable could be height. So is the person 5'8", 5'9", 6'2", 6'3", like that. The independent variable in an experiment, so we've got an experiment, the independent variable is the variable that is manipulated by the experimenter, manipulated in the experiment. It is what the experimenter changes or assigns. So if you've got let's say you've got a research study and you're looking at how 2 different medications affect pain. Your independent variable in that case is the medications. Independent variables can have levels. Levels are the different treatment conditions. So in my example that I just gave, the levels are the 2 different pain medications. If you have a placebo in there, that's another level. If you have a control group that isn't getting anything at all, that's another level. Typically you'd want a placebo in there, but regardless of all of that, you've got the levels of your independent variable, the different pain meds, the placebo, the control group, however you've got it. Then from that, you've got your dependent variables. Your dependent variables are what the researcher is measuring, what the independent variable influences. So the independent variable is manipulated, the dependent variable is measured by the experimenter. It's the experimental outcome. And it is important to note that dependent variables do not have levels, even if it could be, even if you've got different outcomes. Of course, you're going to have different outcomes. Let's say you're looking at pain levels on a scale of 1 to 7, so people can have anywhere from 1 to a 7 as their outcome. That isn't counted as levels, that's just outcomes. There's 2 main types of variables we're going to look at here before we get into looking at different subcategories of variables, but the first 2 subcategories of variables we're going to look at is qualitative and quantitative. Qualitative variable is a variable that varies in kind. What that basically means is varies in type. It does not reflect size or the extent to what's being measured. So if I was looking at auto manufacturer again, Chevy, Toyota, Ford, they're differing in type, they're varying in kind, but it's not reflecting the size of what's being measured. If I assign, you can assign numbers to qualitative variables. If I assign a 1 to a Ford, 2 to Chevy, 3 to Toyota, it doesn't mean that the Ford is greater than Chevy, or that Toyota is greater than Chevy, depending on what direction you're looking at it, because the numbers are just arbitrary, they're just placeholders. On the other hand, quantitative does vary in amount and has magnitude, meaning that it's something like height, weight. Even finishers in a race, they vary in amount. first place is ahead of second place is ahead of third place. As I said, we're going to look at a couple different things for variables. Next thing we're going to look at is when we split it up into discrete or discontinuous and continuous. So a discrete variable is a variable that comes in whole units or categories. Typically it's either there or not, usually is expressed as a whole number. Not always as a whole number, but the big thing with discrete or discontinuous is that it doesn't have an infinite amount between any 2 points. If you hear my cat, I am sorry again. He likes to get noisy when I'm talking, sorry. Okay, so discrete, there isn't an infinite amount between any 2 points. We look at it as, like, let's say children. How many children do you have? You can't have half a child. You can only have 1 child, 2 children, 3 children, 0 children, that type of thing. But you can't have 1.5 children. As I said, there's sometimes where this is the case where you can have fractions for discrete. Let's talk about credit hours that you're taking for classes. In that case, you can have a whole credit, a half a credit. So in this case, it's still discrete because you can have 1.5 credits or 2 credits or 1 credit that you're taking, but you can't have 1.2735 credits. You can't have an infinite amount between any 2 points. There are still fixed amounts. Whereas continuous, on the other hand, does have that. It's got a continuum. You've got fractions, whole units, an infinite amount between any 2 points. Continuous variables are only limited by your level of measurement, meaning your measurement tool. How good is your measurement tool? So if we say height, you say you are 5 foot 9 inches. Well, you might even say you're 5 foot 9.5 inches. That doesn't mean it's not a continuous variable. It's still a continuous variable. It just means that the tool we're using for measurement only goes to inches or half inches. Let's look at some of the levels of measurement. And when I'm saying levels of measurement, I don't mean like I was saying on the last side of tools for measuring. I'm saying levels of measurement as in kind of a little bit the same as that we were just talking about with qualitative versus quantitative. And levels of measurement are looking at the different types of measurements you can do on a variable. This is important because the statistics we do depends on the level of measurement. So the first level of measurement is nominal. Nominal is, it's Latin for nomen, which is name. It's basically the same thing as qualitative variables, meaning it's characterized by a name, it's a category, it's varies in kind, varies in type, that type of thing. So if I talk about auto manufacturer, that is a nominal variable. So one thing that is important for nominal variables is they need to be mutually exclusive, meaning each individual thing can only fit in one category. You can't have a car that's both a Ford and a Chevy. If you did, for some reason, cut in half a Ford and cut in half a Chevy, weld them together, that would actually probably go in a entirely new category of its own, which is hybrid. So you can't have something in two or more categories. It must be collectively exhaustive, as in everything that you're measuring must have a category, meaning if you've now got that car that's welded together with 2 different ones, you need to create a new category for it so that every observation has a category. There is no true zero in nominal. Basically, the numbers don't mean anything. For nominal, if you do apply numbers to it, let's say you apply a 0 to male and a 1 to female when you're looking at differences in sex, that 0 doesn't mean absence of, so there is no true zero. Example here, again, like I just said, sex, political affiliation, auto manufacturer, there's many examples, but the point is a nominal is just going to be categories. The numbers don't mean anything. The next is ordinal. Ordinal is going to be ranked. big thing or to know of or to think about is ranked for ordinal. Ordinal doesn't care about how close or distant different observations are. All it cares about is if you've got a 1, it comes before 2. 2 comes before 3. If you're talking about size, 3 is greater than 2, 2 is greater than 1. But it doesn't say anything about the distance between 1 and 2 and 2 and 3. For ordinal, again, just like nominal, there's no true zero, meaning something applied as 0, it doesn't mean it's the absence of. That's what I mean when I say true zero. It doesn't mean it's the absence of. If somebody is running a race and gets a 0 position, it doesn't mean they've got a absence of running the race. They might have got a 0 or for various different reasons, but the point is 0 doesn't mean the absence of. Some examples: finishing position in a race, your class rank, that's a good one, freshman, sophomore, junior, senior. For that, seniors are beyond juniors, juniors are beyond sophomores, sophomores are beyond freshmen, master's students are beyond seniors. When you've got class rank like that, you're looking at the order that's important, but it doesn't necessarily mean that a senior has finished exactly so many credits more than a junior. It just means that they have passed a threshold and they are beyond that. The next is interval. So interval now takes the ordinal, that is, the order is important, but now we've made equal separation between each value. So the difference between values is known and is consistent. You can tell which unit's greater than others and by how much. However, for interval, there's still no true 0. 0 doesn't imply absence. One of the perfect examples I always give is, let's say I'm standing up next to a desk and I measure my height from the top of that desk, not from the floor, but from the top of that desk. I'm measuring my height from the top of that desk. My height, if I had a 0 height, if I was exactly as tall as the desk, meaning I had 0 height, that doesn't imply absence of height. I still have height, but my height is measured from an arbitrary point along the line, not from true 0. What this means is we can't say that two numbers are in a ratio to each other. We can't say that 100 is twice as large as 50. If my height from the top of a desk is 28 inches, you can't say that I am twice as tall as someone who's only 14 inches from the top of the desk. I'm only 14 inches taller than them. I'm not twice as tall as them. Examples here, things like SAT scores, which don't have a 0. 0 doesn't mean the absence of. Fahrenheit and Celsius, again, a 0 is not the absence of temperature or the absence of heat, if you want to get technical with chemistry. Final one is ratio. Ratio takes interval but adds absolute 0, meaning that we've still got all the properties of interval, that they're in order, the distance between any two numbers is consistent, but absolute 0 is on the line, meaning if you've got an absence of something, if something's 0, it means you have an absence of it. You can then make ratio statements. If somebody is 60 inches tall, they're twice as tall as someone who's 30 inches tall when you're measuring from the ground. So when we look at things like height when measured from the ground, Kelvin temperature scale, most things that we look at, weight, just about everything we measure where 0 is an absence of is a ratio. Let's actually look at some examples here, or kind of look at some questions. So think about these for a second as I'm going through them. First one is marital status. So marital status, married, divorced, separated, single, all of that are different marital statuses. If you applied a 1 to someone who's married and a 2 to someone who's divorced, does that mean that the 2 is greater than 1, that divorce is greater than married? No. So therefore it's nominal. It's categories. They're varying in kind. Olympic medals, gold, silver, and bronze. Now order matters. Gold is better than silver, silver is better than bronze. However, let's say we were looking at finishers in a race. Does the person who got gold, did they finish exactly the same amount of difference as to silver that silver did to bronze? No. So the distance between them is not consistent, is not necessarily known, therefore it has to be ordinal. Next one, hometown. Hometown, just like marital status, we've got groups, we've got categories, nominal. How about number of words remembered on a memory test? If someone remembers one word and somebody else remembers 2 words, the person who remembered 2 words remembered more than one. So order does matter. So we're at least at ordinal. How about the difference between knowing 5 words and 4 words? Is that the exact same as the difference between knowing 10 words and 9 words? Yes. So it at least has to be interval. However, is 0 the absence of knowing any words? Answer, yes. If you remember 0 words, it's an absence of. Because it's an absence of, it's ratio. For very similar reasons, driving speed, order matters, interval is the same between any mile an hour, and a 0 is an absence of driving speed, so again it's ratio. How about I throw one in just to be a little bit confusing? How about IQ? IQ is an interesting one because you can at least say that yeah, order matters. An IQ of 110 is greater than an IQ of 109. Some would argue, on one hand, that well, let's even just jump to the other side. Let's jump. Is it ratio? Is 0 IQ the absence of IQ? The answer there is, from what we know from IQ tests, no. It just means you're not measurable. It doesn't mean it's an absence of intelligence. Some would argue yes, but the answer is no there. So it's not ratio. So now it needs to either be ordinal or interval. And this is where I'm throwing this one out there as a curveball to show that these orders of these levels of measurement aren't always consistent, because some people would say that the difference between someone that's 100 and 110 is the same as the difference between 110 and 90. Others would say that's not the case. So because of that, it could be interval, it could be ordinal. I am not going to ask you questions like that on an exam or a quiz, but I just want you to be aware of the fact that there are things like this out there that are tough choices, and there isn't necessarily one correct answer. Okay, let's transition into some other things relating to this: population versus sample and parameter versus statistic. So a population, as we already talked about, complete set of data that we're interested in. Complete set, everyone that's possible for us to be interested in. If we were interested in the average height of Detroit Mercy students, the population would be all Detroit Mercy students. From the population, we have parameters. Parameters is any number applied to the population that quantifies it. Basically, if we know the average height of Detroit Mercy students, that is a parameter. If we know the variance, the variability of height in Detroit Mercy students, that is a parameter. However, we cannot always sample the entire population. It's rare that we can get data from the entire population. It's usually too expensive, too time-consuming, or just impossible. So therefore, we take samples to make inferences about the population. A sample is a subset of the population that theoretically bears the same characteristics. So we take a sample from the population and we run our analysis on that sample. When we have a sample, any variable applying to the sample is considered a statistic. So let's say we take 20 Detroit Mercy students, we get their height, we get the average height of those 20 students. That is a sample statistic, that average height. If we get the variability in their height, that's a statistic. One key question we have to ask ourselves, though, is our sample representative of our population? Because to do inferential statistics, our sample needs to be as close to our population and representation as possible. In theory, and I'll talk about it a little bit on the next slide, but in theory, we like to think that they're closer than they are, but in general, they're actually probably not as accurate as we would like. That's because a lot of studies are done on college students, and then inferences are made about the population as a whole, and there's differences between college students and the population as a whole. But let's look at some things we can do to make sure our sample is representative or more representative. First thing we can do, random sampling. This is where every member of the population has an equal opportunity of being included in the sample. As I just said, most studies are done on college students. If the population is everyone in the US, then everyone doesn't have an equal chance, so most studies are not doing random sampling. But a true random sample, everybody in the population has an equal chance of getting in. If you do that, that makes it so your sample is more likely to be representative. Then let's say we've got multiple levels of our independent variable. We need to do random assignment such that each individual in the study has an equal chance of being in each level of our independent variable. That reduces between group differences due to sampling. So if let's say we took the first 10 people and put them in group 1 and the next 10 people and put them in group 2, well, something about when we were collecting it, let's say we collected the first 10 in the morning and the second 10 in the evening, well, there could be individual differences between those that cause people to be morning people or evening people, which could result in a confound. It could result in messing up our differences where our sample doesn't become representative. So random assignment, each person selected has an equal chance of being in each group. After all that's done, you still are going to have sampling error. When we come back to probability, we'll talk about sampling error again, but sampling error is the difference between your sample statistic and the population parameter, and you will always contain sampling error. You are not going to get 100% representative of the population. Just by the nature of it, because you're not collecting the entire population, you're going to have slight differences between your sample and your population. Your objective as a researcher is to minimize the differences between your sample and your population, but you're never going to be able to completely eliminate them. That leads to sampling error. And as I said, when we get to statistics, when we get to probability, we'll talk about sampling error again, because sampling error is actually, we can estimate sampling error, and we estimate sampling error using probability, and that allows us to make inferential statistics. Let's get into those two terms again real quick for just a second. That is descriptive and inferential statistics. You've heard me use these terms over and over again. So descriptive statistics are essentially organizing or summarizing the data that you have. So you've got data, you've got a sample, we're using descriptive statistics to describe it. You see here in the bottom where we've got some NFL descriptive statistics, we've got their position, a nominal variable, we've got the yards that they ran, which is a ratio, yards per carry, another ratio, touchdowns, another ratio. But the point is you've got these different descriptive statistics. You're describing your data. Even if you took an average of the yards, an average of the yards per carry, an average of the touchdowns, those would be descriptive statistics as well. They're describing the data. Anything that we have that describes the data we have is descriptive statistics. Sorry about the squeaking when I write sometimes. The pen on the art pad that I have sometimes squeaks when I'm writing, and I know that comes through the microphone, so I apologize. On the other hand, inferential statistics are when we take the sample, we take those descriptive statistics, and then we make inferences about the population. So we use the sample, we do inferences about the population. Everything we're going to do in the second half of the semester is going to be inferential statistics. These are the statistical tests that we do when we are basically making or doing hypothesis testing to make inferences about the population from the sample data we've collected. All right, let's transition into some basic math stuff real quick. I know there was some basic math stuff in the other one, but there's the basic math before we get to summation notation, which might be new to some of you. But there's two things I want to look at real quick. First is true or real limits. So this is going to be related to a range of numbers within which the exact number exists. How do we calculate this? We do a number plus and minus 1/2 the units of measurement. Why do we do this? Well, because we want to be as accurate as we can when we're doing statistics, so we need to know the real limits of what we're measuring. So let's say we are measuring weight, and our scale only does whole pounds. And you come up and you're 150 pounds. Well, what are the real limits of that? You take your unit of measurement, and your unit of measurement is going to be your lowest level or your farthest right level. If we did something like 1.00 is our number, our unit of measurement is going to be the hundredths position, because that is the lowest level that we're measuring. So you take our unit of measurement, in this case over here the ones, and then you'd add and subtract 1/2 of that unit. So the ones unit, 1/2 of it is 0.5. So we're going to add and subtract 0.5 to it. So we've got 149.5 and 150.5. We subtracted 0.5 from 150. We added 0.5 to 150. Again, 1/2 of the unit of measurement. The unit of measurement was the ones. 1/2 of that is 0.5. We added and subtracted 0.5. Now our real limits for your weight, if your weight is 150, your real limits is going to be your actual true weight is going to be somewhere between 149.5 and 150.5. The other thing I want to talk about is rounding. We're just going to use the general rule in here. The general rule is, and as well as not just the general rule, but we're going to use it. If you've got less than 0.5, you round down. If you've got 0.5 or higher, you round up. We're going to use that basic rule. There's actually a rule that we use in statistics. So if you go on to do advanced statistics, there's a rule, a special rule, because the problem is with that rule right there is 0.1, 0.2, 0.3, 0.4. I'm just going to write them all here. 0.5, 0.6, 0.7, 0.8, 0.9. And 0. All of these end up as 0. So you've got 1, 2, 3, 4, 5 that round up and 1 that stays 0. But you've got 5 here that round up. You've only got 4 that round down. What ends up happening there is you get a bias in rounding. Your bias is towards rounding up. When you're only doing a little bit of rounding, that doesn't really matter. When you're rounding hundreds, thousands, tens of thousands, millions of times, let's say like with a bank that's rounding fractions of a penny, when you're doing thousands, tens of thousands of roundings, you get this bias towards rounding up, and the bias towards rounding up is not necessarily a good thing. So what the special case, you don't need to know it for in here, but if you do go into advanced statistics, there's a special rule for sometimes with 0.5 you round down and sometimes you round up. So half of the time with 0.5 you round down and half of the time you round up. Again, I'm not going to go into it, but at least know how to do the basics of rounding. But now we're going to talk about this, and that is the general rule here. And that is round to 4 decimal places when doing a problem, round to 2 decimal places at the end of the problem. For everything in this class, when you're doing your homeworks, when you're doing the problems, that's what I would like you to do. It's going to be a general rule of give me the answer rounded to 2 decimal places. So the general answers are going to be rounded to 2 decimal places. However, if you round to 2 decimal places at intermediate steps of the problem, so when we get into these problems, you're going to see that there might be 5, 10, 15 different steps you're going to do as part of the problem. If you round to 2 decimal places at an intermediate step, your final answer is going to be off because of rounding. I'm not real picky about it, but at the same time, to have it correct, what you should do is round to 4 decimal places on intermediate steps, then 2 decimal places at the end. Okay, let's get into the last thing we're going to talk about, and that is summation notation. So the summation notation is basically looking at one of the most important things we're going to use in statistics. If you've never seen it before, the summation notation is right here. And this is the sum symbol right here. So the sum symbol basically means you sum or add everything after it, or everything that's relevant. Important things for us in here, we're going to have x and y for variables. N is going to refer to number of observations. You've got a capital N for population, a lowercase n for sample. We'll have that more later. If you see this with an I like this, xi and yi, that's just the score for an individual person. So if you had x1, that would be the score for person 1. y1 would be the y score for person 1, or for individual or observation 1. And I shouldn't have to say this, but rules of operation are important. Parentheses, then exponents, then multiplication, division, then addition and subtraction. So that's important going ahead, and that is even important within the summation notation. So when you've got various different things, you do them, and then you do them left and right within there. So when we see them, and you're going to see them on the next slide, some examples, you know when to do which step based on the order. Let's look at that. I know I might be a little confusing there, but this first one. So before I even get any farther, that summation notation looks kind of like this. You are going to usually have a variable over here. As I said, you might have an I there. That I just, if you've got an I, it means for all observations or for each individual X observation. But now down here, you might have an I equals. Like see here, you've got an I equals 1. In that case, I equals 1. Whatever here is what you start with. If there is something down there. There doesn't have to be something down there. You might just see the summation notation like this. If you see the summation notation like that, you assume that the I that isn't present below it means start at the beginning. Then you'll have a number that's on top. This number that's on top is the number, let me do number, let me even just erase that, number of observations to count. So that is this one right here. So for this one right here, you're starting at 1. So you're starting at the first observation. So you're starting at person 1. And you are going 2 observations. So you're doing the first observation and the second observation. If it says N on the top, like you see in number 2 here, that means go to the end. So this one is starting at 3, which is right here, and going to the end. So it's got 3 and 4. This one that you see here is your standard way to say it. It's the equivalent of what I've got up here. That is, you start at the beginning and you go to the end. You've got 1, 2, 3, and 4. All of them. So summation notation, you're typically going to see me writing it like it is up in the top left up here. But if you do see a number below it, that's the observation you start on. And if you see a number above, that's how many observations you go. Or if you've got a N up there, you go to the end. Now, there's 3 things you see here on this slide. The 3 things you see here on this slide is this. They're basically, this first one is doing the sum of x, but it's only starting at 1 and going 2 observations. So you're taking the value of x1 and the value of x2, which is 4 and 9. That's what we've got here. X score for 1 and X score for 2. You've got that 4 and the 9, and then after you get them, you sum them together. You add them together. That's what the summation notation is doing, is adding them together. In the second one here, Now we are looking at something a little bit different. We've got the sum of x squared. Yes, we're starting at 3, we're going to the end, but we've got x squared. Order of operations when we're doing math means we do exponents first. So summation is a sum, we do exponents first. So we take x squared for the third observation, because we start at 3, and x squared for the fourth observation. I like to start a new column. And x squared, for here you've got 4 squared, or 16. So for person 1, you've got 4 squared, which is 16. For person 2, you've got 9 squared, 81. Person 3, 6 squared, 36. Person 4, 8 squared, 64. And that corresponds to these two numbers here, because this is person 3's x squared and person 4's x squared. So if you see this like it is here, sum of x squared, you square the values first. So we squared them first, then you add them together, so we get the score of 100. This final one, it's just the basics. We already kind of did that, just the sum of x, but now it's sum of y. But you start at the beginning, you go to the end. We take all the different y observations here, we sum them together, and we get a total of 21. You'll sometimes see that written down here, which I believe you'll see on the next slide how that's sometimes written. Okay, let's look at a couple rules here. We're going to start with number 1. You see I drew a thing all the way over here, and you've got a total column. I like to just fill in the totals, so let's sum up x. Let's add up together all the x's. We add up 4 plus 9 plus 6 plus 8, we get 27. We add up 5 plus 3 plus 7 plus 6. For y, we get 21. If I can get this to work. So that's the basic there, but now let's actually look at this number 1. So there is multiplication occurring. It's 2 times x. Because there's multiplication occurring, we do the multiplication before the summation, order of operations again. So let's take and make a column 2 times x. So we're going to take each x value and multiply it by 2. So first the 4 times 2 is 8, 9 times 2 is 18, 6 times 2 is 12, 8 times 2 is 16. Now we are going to sum them together, add them all up. We get 54. We could also do it like this. It's equal to 8 plus 18 plus 12 plus 16, but it's equal to 54. So the sum of 2 times x is 54. In number 2 here, you see that there's parentheses here around the sum of y before the squared. So if those parentheses weren't there, you'd do y squared first. But because the parentheses are there, what that means is you do the summation first, because you do parentheses first. So you take and do the sum of y first, which we already did here. It's going to be equal to 5 plus 3 plus 7 plus 6. Then that is squared. So it's going to be equal to 21 squared. Let's look at the next one. The next one is kind of, now we've got parentheses around a bunch of different things, but we need to do them in order. First, we've got our exponent. Then we're doing our parentheses first, so we're doing our exponent. Within that, we're doing our exponent first, and then we'll do our subtraction. So we're going to take and do y squared first, our exponent. 5 squared is 25. 3 squared is 9. 7 squared is 49. 6 squared is 36. Now, we need to, before we add these together, we need to do y squared minus y. So we need to take this 25 here and subtract the 5 there. 20. we need to take this 9 and subtract the 3, which is 6. This 49 and subtract the 7, 42. 36 we subtract, because again, we're taking our y squared value and subtracting our y value. So 36 minus 6 is 30. Now we can sum them together. So we've got 50, 92, 98. So we get here 98, and that was this value here. Okay, let's real quick do the last one. Number 4 is easy because we do not have parentheses around the sum around the x minus 10. So we do order of operations, and if you've got the same, you do from left to right. So we do this first. We do the sum of x first. That is this 27 we got up here. So it's 27 minus our 10, or 17. Again, order of operations is important. We don't have parentheses around the x minus 10, so we do the sum of x first, then we do the minus 10. Real quick, just some rules of summation. I've gone a little bit longer on this lecture than I wanted to, and I have a few slides still to go, but I just want to look at some rules of summation. So the sum of a constant is equal to the sum of n times the constant. We'll look at that on the next slide. The sum of a constant times x is also equal to the sum of x times a constant. And finally, the sum of x plus y is equal to the sum of x plus the sum of y. Here, with this last one, it's all addition. It all ends up being the same. However, the sum of x times y is not equal to the sum of x times the sum of y, because in this case, and we'll look at it in another slide, in this case you're doing addition then multiplication. In this case you're doing multiplication then addition. Let's look at those. Let's look at an example first. The sum of a constant equals the same as n times the constant, where n is the number of observations. So here we've got a constant of 10. If we had 4 observations, so our n is 4, we've got 10, x1 is 10, x2 is 10, x3 is 10, x4 is 10, it equals 40. We could also do the constant, which is 10, times our n, and get that same 40. So it comes out the same. Next one, that the sum of a constant times x is the same as the sum of x times the constant. So let's first take and look at summing our constant here. So summing our constant, this is the same one we did before. Summing x is 27. However, down here on the bottom, we took that sum of x and multiplied it by 10, we get 270. However, if we take that same constant and multiplied it by 10 times x, so multiplied it by each one, we'd get 40, 90, 60, and 80. That is this one right here. 40 is x, which is 4 times 10. Down at the bottom, 8 times 10 is 80. We add those together and we get the same value. So you can do it either way if you're multiplying by a constant. If your c is not, if you don't have a constant there, but you've got some other value that's changing, you can't do that. But if it's a constant, you can pull it out. Next one, sum of x plus y is equal to the sum of x plus the sum of y. Again, let's actually just do x plus y here. So x plus y for this first one, 4 plus 5 is 9. 9 plus 3 is 12, 6 plus 7 is 13, 8 plus 6 is 14. If we sum these together, we get 30, 40, 48, which is right here. However, if we take our total here, which was 27, our total here, which was 21, we add those together, we also get 48. And again, this is because everything here is just doing addition, so the order you end up doing it in doesn't matter as much, or doesn't matter here. However, on the other hand, the sum of x times y does not equal the sum of x times the sum of y. Let's do that real quick. X, y here, x times y, we've got 20, 27, 42, and 48. We sum those together, we get 137 here. And that's what's right here. However, if we take our 28 and our 21 and multiply them, we get 588. They are not equal. So when you're doing summation, if you've got multiplication, you can't pull them out and do them separate. That's because, as I said a little bit ago, in this case, you're doing addition first. So you're doing addition here, then you're doing multiplication. Whereas in this one, you're doing multiplication first, then you're doing addition. I hope that makes sense. Final thing just to talk about real quick, it's just ratios, proportions, percentages. This you should already know, but if you don't, it's just something to look into, because when we get to things like probability, you'll need to know these. So let's say we have 200 animals, 130 are cats and 70 are dogs. The ratio of cats to dogs is 130, if I can make it 3 right, to 70, or 13 to 7 if we reduce it. If we take and do proportions, so the ratio is 13 to 7, but proportions, that is what it proportion is cats, we would take our 130, our number that's cats, divided by our n, which is our total, so n equals 200. Let's say x1 is cats, and or let's say x is cats and y is dogs. So to get a proportion, you take your number of that variable and divide it by n. So in this case, it would be equal to x divided by n, or 130 divided by 200, and we get the proportion that's cats is 0.65. Dogs, that is equal to y divided by n, or 70 divided by 200, which is 0.35. Your total proportion should add up to be 1.00 if you've got categories for everything. You then can take those proportions and turn them into percentages by multiplying them by 100, so that 0.65 times 100 is 65%, the 0.35 times 100 is 35%. Again, this should be all stuff you already know, but if you don't, or if it's been a while, this is basically a refresher for that. So just in review, we looked at research in the behavioral sciences, we looked at some basic terminology for stuff you're going to expect to have this semester, we looked at descriptive versus inferential statistics and how that's going to play out this semester, and then we finished with some math stuff that should aid you in doing the math that we're doing. I put in the summation notation because just about every statistical test we're going to use is going to use that summation notation. That's why we cover it here. Okay, thank you.